Hi, today we're going to look at a line integral and we're going to do something interesting with it. You'll notice when you read this, they're asking us to compute this line integral. Here's our vector field and it says where C is a path from 1, 1 to 4, 2. So that's a little bit different than what we've seen before because normally we get a specific function R of t that defines the path from 1, 1 to 4, 2. So given we have this freedom, I'm going to start by making a line. Okay, so how would you make a line between 2 points? First thing I do is I would write my line like this. I'd say R of t equals the starting vector, which I'm going to make 1, 1. And then it's plus some parameter t times a direction vector. So to get a direction vector, you just ask yourself what vector would you have to add to the point 1, 1 to land on the point 4, 2. And that would be the vector 3, 1. So there you have it. If you want, you could write this in parameterized form now, which is going to be helpful. So we'll say x of t is equal to 1 plus 3t. That comes from just taking the 1 from this vector and the 3t from that vector. And then we can say y of t is equal to, and then we'll take the 1 from this vector and the 1 from that vector multiplied by t. So you end up getting 1 plus 1t or 1 plus t. And then if you think about it, if we want this line to start at the point 1, 1, then we'll just let t equal 0, because if I plug 0 here and here, I would just get 1, 1 back for x and y. And then if I plugged in 1, I would go the full length of this direction vector and land over here on the point 4, 2. So this becomes my parameterization. So what I'm going to do now is evaluate this line integral. We need this vector field and we need this parameterization. So let's go do that. So first things first, remember if we're going to do a line integral of f dot dr, we've shown in prior videos that it's the nicest way to do that mechanically is to take r of t, plug it into f, so you're rewriting your vector field as a function of t, and then dot that with the derivative of your parameterization dt. Okay, so let's not forget f of x comma y in this particular problem was x minus y times I plus x minus 2 times j. And our parameterization is just x of t equals 1 plus 3t and y of t equals, 1 plus t. And the domain for t is greater than or equal to 0, is greater than or equal to 1. So let's use this stuff and all that other stuff and go to work. So integral 0 to 1, f of r of t means wherever there is an x, we're going to put 1 plus 3t minus that y minus 1 plus t times I plus x minus 2, so 1 plus 3t minus 2 times j. And then that whole thing is going to get dotted with r prime of t, but r prime of t is just a derivative of this parameterized function. So the derivative of the first component, the x component, is just 3. I'll write this as a vector, 3. Actually, let's be consistent with my notation. Instead of writing it that way, let's write it in this vector notation. We'll just write it 3i plus, and then your derivative of the y term is just 1, because you can see there's a 1 in front of that t. So it's going to be plus 1j dt. Okay, so let's actually simplify things and start to work on this dot product. So this thing here, if we simplify, you can see that the 1's will cancel. You end up with 3t minus t, so that's just 2t. Over here, you've got 1 and negative 2, that's negative 1, so you get negative 1 plus 3t. So this integral becomes the integral from 0 to 1 of, what do we got here? Bracket, open parenthesis, 2t times I plus negative 1 plus 3t times j dot this expression. Okay, Great. So if we find our dot product here, we multiply those components together, and let's be careful with my parentheses there, and then we multiply those components together, and then we add them up. So we would get, in this case, we'd have 2t times 3 is 6t plus, and then if we took this times 1, we just get negative 1 plus 3t. We bring down that dt, and then we're going to integrate from 0 to 1. Oh, that's a t there. All right, let's simplify a little bit more. Integral 0 to 1, so we have 9t minus 1 dt. Okay, so this is a pretty easy integral. Let's try not to make any silly mistakes. So we're going to get 9 halves t squared minus t, evaluated from 0 to 1. We'll plug in 1, we'll get 9 halves minus 1. We plug in 0 to these things, we just get 0, so there'll be minus 0 here. 9 halves minus 1, 7 halves. So that's the value of our integral. So it's positive. That means that the vector field did some work to us as we helped us out a little bit along the way as we moved along this path. Okay, I'm going to go back and just emphasize the freedom that was given to us in this problem. They see here where C is a path from 1, 1 to 4, 2. I didn't have to use a line. I could have done something something pretty nice. Here's a going from 1, 1 to 4, 2. When I look at that, I notice that that the y values here, I just happen to notice this, is the square root of the x value. 2 is the square root of 4. 1 is the square root of 1. So here's another parameterization that would work. X of t, I'll just write x, yeah, x of t could just equal t, and y of t could be the square root of t. And then I'll make sure that t goes from 1 to 4. And you can check this parameterization. So for example, if you did x of 1, you'd get 1. Y of 1 would be the square root of 1, which would just be 1. So I'm plugging these things in here. And then similarly, if I did x of 4, right, I'm going to plug these things in here, I would get 4. And y of 4 would be the square root of 4, which would be 2. So sure enough, this parameterization with this domain here will go from the point 1, 1 to the point 4, 2, just like we asked, like we requested. All right, so I'm going to redo the line integral again using this new parameterization. So let's remind ourselves our function here, f of x comma y, was x minus y times I plus x minus 2 times j. And so I'm going to just start to work through the line integral. So it's going to be integral 0, or not 0 in this case, sorry, because our domain has changed. Our domain is going to go from 1 to 4. We're going to plug these things here into here and write f of r of t. That's how we refer to it. So it's going to be, here we go, t minus square root of t times I plus t minus 2 times j. And then we have to multiply this by r prime of t. Well, the derivative of, we look up here again, just look up here, I'm circling it in green. The derivative of x of t equals t is simply 1. So that's going to be 1i plus, and the derivative of square root of t is, however you want to write it, we could write 1 over 2 square root of t times j dt. Okay, so now I'm going to start working through this. If we do our dot products are we multiply the x components together, multiply the y components together, and we add them up. So the first one's going to be easy. It's going to be t minus the square root of t, and then we're going to have a plus here. Let's do our integral from 1 to 4. And then if we multiply these blue things together, we end up with t times 1 over the square root of t. So that's actually the square root of t over 2 minus if we multiply 2 by 1 over 2 square root of t, you can see those 2's would cancel. We get minus 1 over the square root of t. And then we have a dt here. Okay. So let's see if we can combine anything. We actually combine those two middle terms there. Integral from 1 to 4t minus square root of t over 2 minus 1 over the square root of t dt. All right, so this is just do a little bit of bashing here. Integral 1 to 4t minus, oops, sorry, that looks like equals. Let's fix that up. All right, so that's going to be minus 1/2 t to the 1/2 minus t to the negative 1/2. So this is about rewriting our exponents. And now we're ready to do our antiderivatives. So here we go. This becomes 1/2 t squared. And then here, just I'll do this carefully. You have negative 1/2, and you're going to take this exponent 1/2 and add 1 to it. So that will become t to the 3/2, and you have to divide by a new exponent of 3/2. So really, if you're dividing by 3/2, you're multiplying by 2/3. So you end up with 2/3 times negative 1/2 times t to the 3/2. And you can see that that would give you negative 1/3, because the 2's would cancel here and here, t to the 3/2. And then for my last answer there, for this thing, I'll underline it in blue. If we add 1 to the exponent, you get t to the 1/2. You divide by a new exponent 1/2, which is really the same thing as multiplying by 2. So you get 2t to the 1/2. So minus 2t to the 1/2. Yep, I'm just checking that sign there. But when we add, yeah, it is actually still minus because there's a minus here. When we deal with just this part, we get positive 2t, and then it's being subtracted. All right, so we're all set. This is going to get evaluated from 1 to 4. So if we plug 4 everywhere, we get 1/2 of 4 squared, or 1/2 of 16. I guess I'll just plug it all in first, and then we'll see what happens. Get that, and we do minus. We're going to plug in 1 everywhere. At this point, maybe you just go plug it in the calculator. I will bash through it. Why not? So there's lots of places to make a small error. Hopefully I didn't make anything. So in this first case, we end up with 1/2 of 16, so that's going to be 8. Minus, now 4 to the 3/2 power. Don't forget the bottom of a fractional exponent is the root. So the square root of 4 is 2, and then I'm cubing it, which gives me 8. And then I'm multiplying it by 1/3, so I get 8/3. And then over here, I got the square root of 4, because that's what 1/2 power means, times 2 is going to be minus 4. And I have minus. Plugging in 1 is easy. I just get 1/2 minus 1/3 minus 2. So let's do this. 8 minus 8/3 minus 4 minus 1/2 plus 1/3 plus 2. So I'm just going to put together the things that I want to put together here. 8 and 2 gives me a 10. We've got the negative 8/3 and positive 1/3. That would give you negative 7/3. And actually, I forgot about the minus 4. Well, the minus 4, I should have just dealt with that. Okay, so we'll deal with that in a second. Minus 4 minus 1/2. So what do we have now? 6 minus 7/3 minus 1/2. I guess your common denominator is going to be 6 here, right? Everything's going to be over 6. And so this is 3/6. This is 14/6. You can see I multiply top and bottom by 2. And then this is 36/6. So if we were to just subtract that carefully, we'll get 36 minus 14 minus 3. So we end up getting 19/6. Okay, so good times. We did a whole bunch of work. Here's the most important thing. What we just noticed is that we did the same line integral of the same vector function between the same 2 points, but we took different paths. So from a picture point of view, what we really did was we went through a vector field. We went from the point 1, 1 over here to the point 4, 2. We did it 2 ways. We did it with a straight line, And we did it with a square root function, which would look like this. And we just showed that in the square root case, we got, I think, an answer of, just so I don't forget, hope that's the other one, sorry. We got 19/6. And we just saw a moment ago for the line integral with the straight line, we got 7/2. So what that means is that different amount of work, we get different amounts of assistance done to us depending on the path that we took. So this is really important. This brings up the idea of something called path independence, which, by the way, is not the case in this problem. What we've just shown is depending on the path you take between the 2 points, you get a different value for your line integral. So what we say is that moving through this vector field, the vector field we have here is this, f of x comma y equals x minus y I plus x minus 2 times j, that this vector field, and we're going to move between 2 points, doesn't have the property of being path independent. In other words, if you pick a different path to go through to go between 2 points, different amount of work is going to get done to you by the vector field. And we'll investigate that more in the future. Thanks for watching.